Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we look at the implementation of logistic regression in Python. In previous video, we looked at the intuition of how the logistic regression works. So now we'll do the actual coding and see how we can classify certain data set. So let's get into Jupyter Notebook and start coding. Here I've imported a couple of libraries, NumPy, Matplotlib, and these sklearn libraries. And let me run that cell. And then these are the versions I'm using. For data, we'll start out with using the iris dataset. So we'll create a variable data is equal to data sets dot load underscore iris. And within this, we can then look at what the dataset has by using DESCR. And here, as you can see, there are these four columns that are numeric, which is the sepal length, width, and then petal length and width. And then we have this last column, which is a class. So there are three classes and not two classes. So this would be a multi-class classification problem where we have the class Iris setosa, Iris versicolor, and Iris virginica, three classes. So let's see how we can work with this data set and classify these three classes. So we'll split the data into train and test sets here, as we have done previously with X train, and then we have this Y train, and then we have this Y test is equal to train underscore test underscore split, and this will be from data dot data and then data dot target. So once we have these, we can also get the class names. We already know what they are, but just to make sure we know them, we'll use the class names is equal to data dot target underscore names, and we can print class names. So just type class name, and these are the names of the classes: setosa, versicolor, and virginica. So this would be 0, 1, and 2. Now let's use logistic regression first, and then later on we'll look at how we can implement stats model as well. So for logistic regression, I'll create a variable CLF is equal to linear underscore model or logistic regression, and here we have random underscore state is equal to 0. Then we have max iteration is equal to 200, and we have penalty is equal to L2 penalty, and that's the default. Again, multi-class, this is multi-class, so we can specify which method. The default is auto, and it would select this, but I'm specifying OVR, which is one versus rest. And we have the fit underscore intercept is equal to set to true. That's also the default value. Once that is done, the next step is CLF is equal to CLF dot fit x train and y train. And after this, we have y underscore pred is equal to CLF dot predict. And here we can use the x, the tests data set x test. And finally, we have the scores, CLF dot score, and this would be x test and y test. So we are just trying to figure out the accuracy here. And when we run this, we see that there is a 94% accuracy. Now if we run this again, we get the same because we have set the random state is equal to 0. Now to check the classes, we can check again clf dot classes, and here see that there are three classes: 0, 1, and 2. Now we can plot the classification in form of a confusion matrix. So confusion matrix. So what this is a way to visualize how many classifications were correct and how many data points were misclassified. So to create that, we can use confusion underscore matrix. So let's call it, I'm going to call the CM is equal to matrix dot confusion underscore matrix, and this needs the original true data, so that's the y test, and then we have y pred, which is the predicted values. Now if we print the confusion matrix, so let's go ahead and do that. Print, and this is confusion matrix, and with this cm as, so this is the confusion matrix where we have diagonally, those are the values that were correctly predicted for each of the classes, and then these two off diagonal elements are the misclassifications, and we can plot in a more colorful way. So let's try that. DSP is equal to matrix dot plot confusion matrix, and here we have the model CLF, and then we have the x underscore test and y underscore test, that's the data, and display underscore labels. So here we can specify the labels that we have created earlier, so which are these labels that we put in, that we have put in the variable class underscore names. And in addition to this, we can specify the color, so let's say plt dot cm blues, and when we run this, so let's check what it's name without an s, so name without an s. So this is exactly what we have up above here in the array or matrix format. So what this is telling us is that uh, for Setosa there were 12 data points, and all the 12 in this case were correctly classified. Similarly, so Setosa is right here. So there were 12 labels, all of them were correctly classified as 12. For versicolor, there were 9 plus 2, the 11 levels, out of which only 9 were classified correctly as versicolor, but then 2 were misclassified as virginica, right here. And for virginica, there were 15 data points, and all of the 15 were classified correctly as virginica. So that's how the confusion matrix can be read. So these are the true labels, and these are the predicted labels. Now let's look at how the score from this particular regression, which is 0.94, and just to make sure where that accuracy score came from, it is the true classifications that we have. So 12 plus 9 plus 15, so those are the diagonal elements, divided by total number of elements, so that is going to be 12 plus 9 plus 2 plus 15, and when we run that, we get 0.947, and that's the output that we got earlier in the score. Now let's compare this with ridge regression that we have seen in previous videos. We'll use the default values just to make it easier. CLF is equal to linear underscore model dot ridge, sorry, this would be ridge classifier and not regression classifier, and classifier, and here we can also specify random state as 0. Now if we say clf dot fit x underscore train y underscore train, and then get the predicted values, y pred is equal to clf dot predict, and we have predict on the x underscore test, and then we have clf dot score, again this would be the accuracy, x underscore test, y underscore test underscore test, and we get a value of 0.8157. So the default value accuracy score is lesser than the logistic regression. But if maybe if the parameters for ridge classifier are optimized, this score could improve further. If we run now, if we run this part, class name is not defined. So if we run this part, here we can see that there are three misclassifications for versicolor as well as four misclassifications for virginica. And for Setosa, there are no misclassifications. All the 12 were correctly predicted as Setosa. That's the difference between those two different classifiers. Now let's look at another data set that we have seen in the previous video where we talked about the intuition of logistic regression. And here we'll import the library statsmodels.api as sm. And we now can get the data, which is we'll store it in the variable spector is equal to sm.datasets.spector.load underscore pandas, and then we have spector dot exog. So those are the predictors in that variable. Sm dot add underscore constant. So what we are doing here is we are adding a column of ones to the data set spector.exog, and so that's what we have. Now here we can go ahead and look into the data set. So if we type spector dot keys, we get these keys. So now we can look into it. So if you say what is in exog, so these are the values. There are three original columns: GPA, TUC, and PSI. And then to that we added this constant term, which is all ones. And so why that is needed is for the modeling purposes. And then we have vector data. Here we get the original data that we have, where the grade column is the one that would be in this e endog. So e spector dot endog, and that's the grade column right there, which is just ones and zeros. And to check how many classes are there, we can look at np dot unique, and we see that it's a binary classification problem with just two classes, the positive class 1 and the negative class 0. And in addition to this, we can also get these names np. So vector dot endog underscore name, so that's the name of the target column, which is grade. And finally let's look at the raw underscore data, and we get the original data that we had. Now let's look at how we can code this. So for the very first thing we are going to do is fit the model. So to do that, I'll create a variable clf underscore s for stats models is equal to sm.logit, and then spector.endog, that's the target, vector.exog. So that's the few predictors. So the dot, this term is the key for this dictionary that we saw above. And then clf underscore s dot fit. So let's say cls underscore s dot fit, and we are going to fit with solver is equal to a bfgs, and then we are going to use that fit for prediction. So y underscore pred underscore s, that's for models, is equal to clf underscore s dot predict, and we are going to use the well, here we did not split the data set into train and test set, so let's leave it at that for now, and print the summary. Clf underscore s dot summary, and so this is summary. Maybe we need to save it into this variable is equal to, okay, so we need to save it in a variable to actually get the summary. And this is the summary that we've seen previously in the video, where we can see that the total number of observations is 32. The pseudo R square value is 0.37. It means that these three predictors or features are able to capture that much variability from the data. So to get it closer to 1, to explain all the variation in the data, there probably needs to be some more features in here. And this is the p-value, which is less than 0.05, which suggests that the fit is reasonable, uh, is significant, or it's good. But the p-value is much lower. It's closer to 1 is considered as a good, sorry, R square value. Then the method used is maximum likelihood estimation. And here we have the p-values which are less than 0.05 alpha value. So therefore these two predictors or features, GPA and PSI, are the ones that are significant in this case. Now if we the as we discussed in previous video, this column is log of odds, and so if we need to get the odds from this one, we need to get the exponential of each of these values. So for example, if we take the exponential of this, then we have 16.87. So what that suggests is that 1 unit increase in the GPA increases the odds of a student's grade to increase by 16.879 times. Now let's create a confusion matrix and see how the classification has worked. So confusion underscore matrix is equal to, so for confusion matrix we need the predicted values, and we didn't create those. So what we could go ahead and do is split this into train and test sets. So let's do that. Put v here, and we have x is equal to spector dot ndog. So, or let's say x underscore train, x underscore test, y underscore train, y underscore test is equal to train underscore test underscore split. And here we have spector dot exog. So that's the those are the features, and then spector dot ndog, those are the target values or the y values that we generally refer them as. And with that we can now change this. So instead of writing this line, I'm going to comment that one out and replace that by a familiar x underscore train. This would be y underscore train first, and then x underscore train. In this case it's Statsmodels, x underscore train. And so that will give us that summary, which would be different. So let's see, must be an unit interval, and we're getting an error with this. So let's check what, oh, I didn't run that cell, that's why. So these are the values we have, and now we could create the y underscore pred. So y underscore pred is equal to clf underscore s dot predict, and we are going to use the predict using the x underscore test that we have. And so we get the we get the predicted values there. Why don't we also get the confusion matrix? I'm going to simply copy all of this so we don't have to type it. Variable names are the same, so it shouldn't matter. So here we need to change this to clf underscore s, and so that gets us the y pred, and then here I'm going to use the matrix underscore accuracy score, and here we have the y underscore test, and then we have y underscore pred dot round, and we get a value of 1. So the values for y underscore test and pred look to be identical. So we have these values for the test and y underscore pred dot round, we get the same value. So that's why it's like perfect accuracy. And here I'm going to change some of the things here. We have the confusion matrix. So that's because this should be again round. And we see that the four the diagonal elements are there and the off diagonal elements are 0. That's like 100% accuracy. Now let's see how we can apply the scikit-learn libraries logistic regression for the same data set. So scikit-learn logistic regression, and for this we'll again use the same spector sm.datasets dot spector dot load underscore pandas. We get that data set, and then going to create the x and y. So spector dot exog, and y is spector dot endog, and with that we can create the x train, x test, y train, and then y test is equal to train underscore test underscore split, and this would be x and y that we have created. And next step is the same as we have done previously, linear underscore model or logistic regression, and within this I'm going to use fit intercept is equal to true, c is equal to 1e9, and the reason for this is to see if we can get a value of coefficients closer to what we have seen for the stats model. And clf underscore fit is x underscore train, y underscore train, and then y underscore pred is equal to clf dot predict, and here we have x underscore test, and so clf dot or we can just use the same, let's use the same metric, and here we can get the score y test y pred. So we go ahead and run this, we get accuracy of 0.875, so a little less than what we have seen before. And again, if we plot the confusion matrix here, we should be able to see there is one there are several misclassifications. So 7 of them are in this particular case. There's one misclassified out of the 8. If we run this again, so if I run this all, we get a different set of result here. So we have these 7 classified correctly, and we have one that is incorrectly classified. Now let's, and the one important point to note here is the values for the coefficients. So if we look at clf dot coef, these are the coefficients we have. If we get the round value of this, so the coefficients we have are these, which is 2.93 minus 0 and 1.6. These are completely different from what we have. So this is 2.40 and then 1.86. So we have 1.6 here. This is, however, a negative value. Now if I use that and convert it by using the exponentials and then look at the values, So this we got 16 earlier, and here we are getting 18 for the first one. And with this, we can also look at the intercept value. So CLF dot intercept or constant intercept underscore. So that's the value we have. And if we get the exponential of that, CLF dot intercept underscore, and we get a value that's close to 0. So that's 0. And this is -10 we have, and here we had the intercept at -11. So the values are not exactly the same, but they should be similar as we see here. Now, before ending this video, let's look at how the logistic regression CV works. So logistic regression CV for cross validation, and we'll use the same spector data set that we have used above. I'll simply copy all of this code, copy that spector with a S, and then copy this conversion where we split the data, and then use this classifier. So that, making the change here, changing that to CV, and then I'll specify 5, a value of 5 for CV, and then I'll just remove this, and so that should be good. Finally, we need the score, and it's already there. So when we run this, we get a accuracy of 1 with the cross validation. And if we try to plot the confusion matrix, we should see no off diagonal elements in the classification. So when we run this part, there is an error, class names. Of course, the class names are not there. So that, and as you can see here, we have 6 and 2. Both the positive and the negative classes are predicted correctly. So before I end this video, I just want to show that the accuracy would be, this would be 6 plus 2 divided by 6 plus 2, and that's going to be 1. So that was it for this video. I hope in this video and the previous video you got a brief overview of what logistic regression is, what classification is, and how we can use the Statsmodels library or the Scikit-learn library to get the values of the odds ratios or the odds or log of odds from logistic regression, and then interpret those to see what the results are telling us, and also use that information to identify some of the features that are significant, or the features that significantly contribute to classifying a particular sample. We also looked at the cross validation using logistic regression CV that has cross validation built in. I hope you would now be able to apply logistic regression to classify a data set that has not only just 2 classes but more than 2 classes. So we saw both binary as well as multi-class classification problems. So I hope you get to do some practice on other data sets. Until then, please like, share, and subscribe. I hope to see you all in the next video. Thank you.